The coming decades will be critical in putting the world on a path toward lower greenhouse gas emissions, especially as energy demand is expected to triple by the end of the century as a result of population growth, increased urbanization, and expanding access to electricity in developing countries. Also, it is evident that Russia's recent actions have necessitated a need for broader access to energy supply beyond a limited source. Yet fossil fuels that shaped the 19th and 20th century civilization can only be relied on at the expense of greenhouse gas emissions and pollution. Given the urgent need for a new large-scale, sustainable, and carbon-free source of energy, the feasibility of nuclear fusion has been demonstrated. To achieve this, however, is no small feat, and for years, even the most renowned researchers and engineers have been unable to generate and supply on a global scale. Despite this, the insurmountable benefits it could provide to our energy sector have resulted in massive funding on a consistent basis. Finally, all the years of persistent shipping have paid off, as Germany's premier plasma research facility appears to have made a breakthrough with a trailblazing new nuclear fusion reactor that is making waves. Our video today looks at Germany's new nuclear fusion reactor, which shocks the entire industry. Be sure to like, comment, and subscribe. Since the 1930s, the theory of nuclear fusion has been a fascination for scientists and engineers alike, who have worked effortlessly towards working to replicate and controlling it. This is due to the fact that nuclear fusion has the potential to produce virtually endless amounts of clean, secure, and cost-effective energy if it can be replicated on Earth on an industrial scale. Unlike fission used in nuclear power plants, where heavy atomic nuclei are subdivided, fusing atoms together in a controlled way releases nearly 4 times as much energy per kilogram of fuel at equal mass, and nearly 4 million times as much energy as a chemical reaction, such as the burning of coal, oil, or gas. Evidently, nuclear fusion is the energy that fuels the stars, and if it could be replicated on Earth, it might be able to supply nearly limitless energy with no carbon emissions and no long-lasting radioactive waste, unlike its polar opposite, nuclear fission, which powers nuclear power plants today. The majority of the fusion reactor concepts in development will combine deuterium and tritium, 2 isotopes of hydrogen atoms with extra neutrons. Ideally, a terajoule of energy, or roughly the amount of energy required by one person in a developed country for 60 years, could theoretically be produced with just a few grams of these reactants. This goes to show the tremendous potential that comes with fusion technology, an ideal game changer, if you ask me. The Max Planck Institute for Plasma Physics researchers have been attempting to replicate the sun's fire on Earth with the hope that a future fusion power plant will produce energy by fusing nuclei of the 2 heavy hydrogen isotopes, deuterium and tritium, to form helium. Hence, with the objective to investigate the suitability of this type for a power plant, the Max Planck Institute for Plasma Physics, which was founded in Garching, Germany in 1960, has introduced the Wendelstein 7X stellarator. What is the Wendelstein 7X stellarator? Greifswald, a small to middle-sized town on Germany's Baltic coast, remains at the forefront of nuclear fusion research, mainly due in large part to the presence of the Wendelstein 7X stellarator. Since generating its first plasma in 2015, the Wendelstein 7X stellarator, an experimental nuclear fusion reactor, has been making impressive advancements toward its goal of providing us with clean, limitless energy. Stellarators are incredibly intricate, twisted, and turned structures that set them apart from the more typical, symmetrical donut-shaped tokamak fusion reactors. The purpose of this reactor, as with all nuclear fusion reactors, is to mimic the processes that take place inside the sun by exposing plasma streams to extremely high temperatures and pressures, which cause atoms to collide and fuse together to produce enormous amounts of energy. Compared to tokamaks, the other primary fusion power technology under study, stellarators have more design flexibility, require less injected power to maintain the plasma, and enable the simplification of some aspects of plasma control. The Wendelstein 7X reactor is so complex that it was designed using supercomputers. It employs 50 superconductive magnetic coils to keep plasma in place, as it loops around a twisting and turning circular chamber. Its developers, the Max Planck Institute for Plasma Physics, recently publicized their new record breakthrough set for the purported fusion product. Even though this measure of performance is based on theory rather than actual physical properties, its essence toward the development of usable fusion power is undeniable. The plasma was heated in these experiments to temperatures of 20 million degrees Celsius or 36 million degrees Fahrenheit, comfortably exceeding the sun's temperature of 15 million degrees Celsius or 27 million degrees Fahrenheit. However, it appears that the Wendelstein 7X may be designed for temperatures much higher than that. This is possible because, when developing the Wendelstein 7X, the engineers set out to address a limitation that distorts the efficiency of classic stellarator designs far more than tokamaks. This issue is a type of heat loss known as neoclassical transport, which occurs when collisions of heated particles dislodge some of them from their orbits and cause them to drift away from the magnetic field. To avoid these kinds of losses, the Wendelstein 7X's magnetic field cage underwent meticulous optimization. Scientists from the Max Planck Institute for Plasma Physics and Princeton Plasma Physics Laboratory conducted a comprehensive new analysis of the Stellarator's round of record-breaking experiments to see if their careful planning paid off. The analysis, which focused on diagnostic data collected by an X-ray imaging crystal spectrometer, revealed a significant reduction in neoclassical transport and revealed that the high temperatures could not have been achieved otherwise. This performance was achieved with modest heating power that is presently available, and the scientists believe with the tendencies shown by the Wendelstein 7X, it is capable of confining heat that reaches temperatures twice as hot as those found in the sun's core in the future. However, as the team pursues nuclear fusion, there are other hurdles in addition to reaching high temperatures, such as addressing other forms of heat loss. With that, more experiments are anticipated before the end of 2022, with a new water cooling system designed to allow for longer experiments. Such innovations have the potential to create an exciting future, one in which clean energy, its security, and widespread availability are guaranteed. Make no mistake, accomplishing this feat will be no easy task, and it may be years before we can make any practical progress. However, the measures being implemented now are small victories that will spur us to develop a new large-scale, sustainable, and carbon-free source of energy. That concludes our video for today. If you enjoyed this video, you should also watch the next video on your screen, which shows China's new mega bridges which